Not least, you've made it to concept 3 notes in our Unit 8 solutions, and we're going to be talking about properties of solutions. So, good news, if you're in my class, we're not going to do any math for this one. So, that's a nice little break. You can do some math for these. So, if you're in a different class, your teacher might be putting some equations in here to add to this. For my class, we're just going to look at this qualitatively. Okay, so here we go. Let's do a little overview of what I mean about properties of solutions. So the presence of solutes affects the properties of solutions. We talked all the way back in concept 1 that because solutions are homogeneous mixtures and they have the same composition throughout, that means they have the same properties throughout. And the presence of solutes in the solvent, like that makes it behave differently than the solvent would on its own. Okay, that's important. But what's really interesting about this is that some properties are not dependent on the nature of the dissolved substance, but on the amount of it. So it's not about what the actual solute is, but how much of it is in there that makes the property a certain way. And so that's what we're going to be focusing on in this concept, because we talked about, properties of matter back in Introduction to Chemistry, like back in that concept 3 of the very first unit. And so I know that you guys can explore those again. Like, that, density would be different. Maybe the appearance of a substance would be different. Maybe the reactivity of the solution is different from the solvent. Like, those are all properties we've already discussed. We have not discussed this type of property or this category of properties. And so that's what we're adding on here. So this concept is not covering every property of solutions. We're specifically going to talk about colligative properties. So these are properties that are dependent on the concentration of the solute particles, not on their identity. Okay, so we're bringing kind of everything we've talked about so far, and we're going to talk about a lot of things that we have mentioned in Unit 7, States of Matter. Okay, so we're going to tie in a bunch of things here. So here's the little overview continued. What we see is that the boiling and freezing points of solutions are different from the pure solvents that make them up. Okay, so what I mean by that is like the boiling point and freezing point of salt water is different from pure water. So a non-volatile solute added to a solvent, what we see the trend is it will lower the freezing point and it will raise the boiling point. What do I mean by non-volatile solute? I mean a substance that has little tendency to become a gas under its existing conditions. Okay, we're going to put it in and it's not going to turn into a gas very readily. Okay, it's non-volatile, but it will change. Its presence will change the freezing point and boiling point. Okay, why? Equilibrium vapor pressure. If you remember talking about that in our last unit. So we're going to talk about that again. So this is vapor pressure is a colligative property. Okay, so vapor pressure, just a reminder, it's the pressure caused by molecules in the gas phase that are in equilibrium with the liquid phase. Okay, so the rate of condensation of going from gas to liquid is equal to the rate of vaporization of going from liquid to gas. Okay, what we see is that as concentration increases, that means the number of solutes is increasing in a given volume. We see that the proportion of solvent, like water, is decreasing. Okay, so if the concentration is getting higher, that's more solute in a given solvent. Okay, so the ratio then is decreasing. So there are less water molecules that can then escape to the liquid phase. Okay, think about that. Less can escape, which means there's less vapor, which means there's going to be a lower vapor pressure. Okay, so the presence of these solutes makes a difference. It impacts the vapor pressure. Solute particles lower the vapor pressure of the solvent. So then we're going to need a higher temperature to bring that vapor pressure up to the atmospheric pressure and cause something like boiling to happen. Okay, and so this is important. Vapor pressure matters because it impacts these other colligative properties like freezing point and boiling point. Okay, so another colligative property. Again, these are properties that depend on the amount of solute, not the identity of those solutes. Okay, is freezing point depression. Okay, so this is the difference between the freezing points of a pure solvent and then a solution from that solvent. So like the difference between the freezing point between water and salt water, okay? It is directly proportional to the molal concentration of the solution. So we're going to always look at molalities here when we're looking at these numbers. And we're not going to calculate these freezing point depressions, but you could, okay? What we see is the greater the solution's molality, the greater the difference in the freezing point of the pure solvent, like the water, versus a solution, like the salt water. So a solution always has a lower freezing point than its pure solvent. So if you add salt to water, it will lower the freezing point of that water. Okay? A solution with an ionic solute, though, and this is where I do want to make an important distinction. It is the amount, not the nature. So you might be thinking, okay, we put salt on roads to help make ice. Excuse me. We put salt on roads to help make ice, melt so that we can drive on roads safely. Why don't we put sugar on roads if it's just the amount that matters, not the actual identity of what we put? Well, think about it this way. Ionic compounds dissociate. So 1 mole of sodium chloride will dissociate into 2 moles of solute particles. We got the sodium and the chlorine. Whereas 1 mole of sucrose stays 1 mole of sucrose. Okay, so with an ionic substance, it has a different amount. And so that's why it creates this different depression level. A solution with an ionic solute is going to produce a greater depression difference in the freezing point than a covalent one because of the ion dissociation, because it's going to create a greater amount there. And the greater the molal concentration, the greater the difference we're going to see in these. Okay, another colligative property goes the opposite direction, and that's your boiling point. Elevation. This is the difference between the boiling points of the pure solvent and a solution from that solvent. And it's also directly proportional to molal concentration. So the greater the solution's molality, the greater the difference in the boiling points between water and salt water. Okay? A solution always has a higher boiling point than its pure solvent on its own. So if you add salt to water, it will raise the boiling point. Okay? This happens because those solute particles, like the salt, it takes up space at the surface where liquid and gas particles meet as things are boiling. And that causes interference. It prevents the solvent particles from escaping to the gaseous state, okay? So it's going to take more heat energy to do that, to change that state from liquid to gas, okay? So we've got vapor pressure, freezing point depression, boiling point elevation, and one last one is osmotic pressure. Now, osmosis may be a familiar term to you. We talk about this in biology, the movement of water from high concentration of water to low concentration of water. So it's balanced on both sides of the membrane. These definitions don't contradict, but we're going to define it slightly differently for the sake of understanding it in a chemistry context, okay? So osmosis is what we see when solvent will move through a semi-permeable membrane from the side of the higher solvent and lower solute, and thus lower solute concentration or molal concentration, to the side of the lower solvent and higher solute, so the higher solute concentration. Okay, that's what osmosis is. It's still the same thing we've learned, higher solvent to lower solvent. But if you're looking at concentration in chemistry, we're looking at the concentration of the solute. So it's actually moving from the lower concentration of solute to the higher concentration of solute. But the property here is osmotic pressure. So the osmotic pressure is the external pressure that must be applied to stop osmosis from happening. Okay, so if we look at this picture, naturally, water is going to move this direction to try to balance out what's going on here concentration-wise. But what we're going to see is, to stop it moving this way, we would have to put a certain amount of pressure to make it stop. And so the greater the concentration, the greater the amount of pressure we're going to have to put on this. So this is a colligative property because the concentration depends on the amount of solute, not the type of solute. But the more solute there is, the greater the concentration, the harder it's going to be, the more pressure that's going to need to be applied to stop this natural movement of solvent from happening. Okay? These are tricky. I feel like these are tricky because they just seem so obscure. And so that is why we are going to do a little research and report activity here where you guys are each going to have a colligative property, one of these 4 we talked about, and you're going to research a real world connection. Like, why does this matter? I think it will make more sense and you'll be able to remember them better if you can associate them with something that is real, that actually happens in the real world. So that is what we are going to do now to wrap up this concept and wrap up this unit.